We now start our discussion on module 2 of chapter 2. Recall that we had defined a measurable set in chapter 1 in this way, that a set A of real numbers is said to be Lebesgue measurable if for any set B of real numbers we have mu star of B equal to mu star of B intersection A plus mu star of B intersection A complement. Now, we had established many properties of these Lebesgue measurable sets, but the definition was too abstract. We had said that we will later give you some topological characterizations of the measurable sets. So, in this module what we are going to do is that we are going to show you that the Lebesgue measurable sets are nearly open as well as nearly closed. So, again see the definition of a Lebesgue measurable set. Mu star is the Lebesgue outer measure on R, and a set E subset of R is called Lebesgue measurable if for any A subset of R we have mu star A equal to mu star of A intersection E plus mu star of A intersection E complement. The only thing we can say about this definition is that the set E has that special property that whenever it divides any set A of R into two disjoint parts, A intersection E and A intersection E complement, we get the Lebesgue outer measure of the whole set A as the sum of the Lebesgue outer measures of the two disjoint parts. But still this definition is very abstract. So, we come to the main result of this module. Following statements are equivalent in the set of real numbers. First, the set E is Lebesgue measurable. Second, given any epsilon greater than 0, we can find an open set O such that E subset of O and mu star of O minus E is less than epsilon. 3. There is a G delta set G containing E such that mu star of G minus E equal to 0. 4. Given any epsilon greater than 0, there is a closed set F such that F subset of E and mu star of E minus F is less than epsilon. And fifth, there is a F sigma set F subset of E such that mu star of E minus F is equal to 0. We start with the proof of the assertion that 1 implies 2. Let E be a Lebesgue measurable set. Let us first suppose that the measure, that is also the Lebesgue outer measure of the set E, is finite. Then we know that given epsilon greater than 0, we can find an open set O containing E such that the set O has this property that mu of O equal to mu star of O, this is less than mu star E plus epsilon. Now, note that O is an open set, so is measurable. By our assumption, E is measurable. Hence, O minus E is also measurable, and we have mu star of O minus E is equal to mu of O minus E, because mu is defined on all measurable sets, and we have already seen in module 1 that the Lebesgue measure is subtractive. So, mu of O minus E becomes mu O minus mu E, and this is less than epsilon, which comes from the above inequality. Now, suppose that E is a set whose outer measure is infinity. Write E n as E intersection minus n n for all n belonging to capital N. See that though E should be unbounded, each E n is a bounded set which is contained in the interval minus n to n, and so mu star E n should be finite, and also since union of all these intervals closed minus n to n is equal to the set of all real numbers R. So, we have E is equal to union n is equal to 1 to infinity E n. Hence, by the first part of the proof, for each n we can find an open set O n containing E n such that mu star of O n minus E n is less than epsilon by 2 to the power n. Now, take the union of all these open sets O n and name it O. Then O is an open set because union of open sets is open, and obviously O contains E, and mu star of O minus E, this is less or equal to sigma n is equal to 1 to infinity mu star of O n minus E n, and this is again less or equal to sigma n is equal to 1 to infinity epsilon by 2 to the power n, and the sum of this series is epsilon. And this proves our assertion 1 implies 2. Now, we go to the assertion 2 implies 3. Let 2 hold, that is, for any epsilon greater than 0, we can find an open set O containing E such that mu star of O minus E is less than epsilon. Now, choose epsilon as 1 by n. Then by 2 we can find an open set O n containing E which have the property mu star of O n minus E is less than 1 by n. Now, take G as the intersection of all these O n. So, G being a countable intersection of open sets is a G delta set, and obviously G contains E, and mu star of G minus E is less than mu star of O n minus E. So, this is less than again 1 by n, and this is true for all n. If we take n tends to infinity, then we get that mu star of G minus E should be equal to 0. We now again come to the assertion 3 implies 1. Suppose 3 holds. What does that mean? This means that there is a G delta set G containing E such that mu star of G minus E is equal to 0. Now, recall that we had seen that if a set has Lebesgue outer measure 0, then it is Lebesgue measurable. So, this set G minus E is also Lebesgue measurable. Hence, G being a G delta set is measurable, G minus E measurable. So, their difference G minus E, which is equal to E, is also measurable. So, we have proved the equivalence of the first 3 statements 1, 2 and 3. We now start with the implication 1 implies 4. Again, let us suppose that E is measurable. Then we know that E complement is also measurable. We have already proved that the assertion 1 is equivalent to the assertion 2, which states that given epsilon greater than 0, we can find an open set O containing the measurable set E such that mu star of O minus E is less than epsilon. So, if we apply this assertion on the set E complement, we get given epsilon greater than 0, there exists an open set G containing E complement such that mu star of G minus E complement is less than epsilon. We write F as G complement. Now, see that G is open. So, its complement F is a closed set. Since G contains E complement, so F is subset of E, and also from the observation that G minus E complement is actually equal to E minus F, it now readily follows that mu star of E minus F, this is equal to mu star of G minus E complement, and this is less than epsilon. We now present the explanation for the implications 4 to 5 and 5 to 1. Now, first consider the implication 4 to 5. For any positive integer n by 4, we can choose a closed set f n subset of E such that mu star of E minus f n is less than 1 by n. Now, we take the union of all these sets f n, that is, we take f as union n equal to 1 to infinity f n. Then f being countable union of closed sets is a f sigma set. Obviously, f is contained in E, and since E minus f is subset of E minus f n for each positive integer n, so by monotonicity of the Lebesgue measure, we get mu star of E minus f is less or equal to mu star of E minus f n, which is less than 1 by n, and this is true for all n, and this shows that we must have mu star of E minus f equal to 0. Finally, we go to the implication 5 to 1. By 5, we have a f sigma set f subset of E such that mu star of E minus f equal to 0. Now, see that since mu star of E minus f is equal to 0 and we know that a set of Lebesgue outer measure 0 is measurable. So, E minus f is measurable. On the other hand, the set f being a f sigma set is already measurable. So, the set E being the union of two measurable sets f and E minus f is also measurable, and this completes the proof. So, from the 5 assertions which we have proved, we can get this important result that the set E is measurable if and only if given epsilon greater than 0, there is an open set O and a closed set F with the property that F subset of E subset of O such that mu of O minus f is less than epsilon, and this shows that a measurable set is nearly open and nearly closed. That is, we can sandwich the measurable set within an open set and a closed set whose difference can be made as small as possible in terms of the measure. Now, we come to an important observation. Generally, continuous functions does not carry measurable sets into measurable sets. There are examples. We will see that if a function has some special properties, then it carries measurable sets into measurable sets, that is, image of a measurable set will also be measurable. Let f from closed interval a b to r be a Lipschitz function, which means that there is a constant c greater than 0 such that mod f x minus f y is always less or equal to c into mod x minus y, and this is true for all x y belonging to closed interval a b. We want to show that first the map F maps a set of Lebesgue measure 0 onto a set of Lebesgue measure 0. Secondly, we will be showing that F maps a F sigma set onto a F sigma set, and finally, with the help of A and B, we will conclude that F maps a measurable set into a measurable set. We start with the proof of the assertion A. Let epsilon greater than 0 be given, and let E subset of A B be a set of Lebesgue measure 0. Now, from the definition of Lebesgue outer measure, we can find a collection of open intervals I k, k belonging to n, which covers E such that sigma k is equal to 1 to infinity L I k, where L I k is the length of I k. This is less than epsilon by c, where remember that c is the Lipschitz constant for the function f. Let a k be the infimum of f x, where x runs over I k, and b k be the supremum of f x when x runs over I k, and this is for each k belonging to n. Obviously, f of I k is subset of the interval a k b k, and this is true for each positive integer k. Now, by the Lipschitz property of f, we already know that for any 2 points u v of the closed interval a b, we have mod f u minus f v is less or equal to mod u minus v into c. Taking the supremum over u v belonging to I k on both sides of the inequality, we have b k minus a k, this is equal to supremum when u and v runs over I k, mod f u minus f v, this is less or equal to c into supremum u v belongs to I k mod u minus v, and this is nothing but c into length of I k. Thus, we have measure of f I k, which is less or equal to b k minus a k, because recall that f of I k is subset of the interval a k b k, and the Lebesgue measure is monotone, and this is again less or equal to c into length of I k. But f e is subset of union k is equal to 1 to infinity f I k, which implies that measure of f e is less or equal to sigma k is equal to 1 to infinity mu of f I k, because the Lebesgue measure is countably subadditive, and this is again less or equal to sigma k is equal to 1 to infinity c L I k, and this is less than epsilon. Now, since epsilon is arbitrary, so this shows that f e is such a set whose Lebesgue measure is less than any small positive number, however small we take it. So, we must have mu of f e equal to 0, and this shows that f takes a Lebesgue measurable set of measure 0 into a Lebesgue measurable set of measure 0. Now, we come to the point b. Let f subset of a b be a f sigma set. We now start with the assertion b. Let f subset of closed interval a b be a f sigma set. From the definition of a f sigma set, we know that there exists a collection f k of closed subsets of a b such that f is the union of the countable number of sets f k. Now, f k being a closed subset of the compact set closed a b is also compact, and of course, it is also closed. Since f is continuous, because we know that each Lipschitz function is continuous. So, f of capital F k is also a compact subset of R, because we know that the continuous image of a compact set is again a compact set, and we know that a set is compact in R if and only if it is bounded and closed. So, f of capital F k is closed. Finally, if we consider f of capital F, so this is nothing but union k is equal to 1 to infinity f of capital F k. So, countable union of closed sets, and hence f of capital F is a F sigma set, and this proves our assertion B. Finally, suppose that E subset of closed interval a b is a Lebesgue measurable set. If mu e is equal to 0, then already we have proved that mu of f e is also 0, and so f e should be Lebesgue measurable. So, the assertion follows from A. Now, let mu of E positive. By the property of Lebesgue measurability, which we have discussed just before this result, we can find a F sigma set F subset of E such that mu of E minus F is equal to 0. But now see that we can write the set E as union of two sets F and E minus F. Consequently, f of E is the union of two sets f of capital F union f of E minus F. Now, since E minus F is a set of Lebesgue measure 0, so by part A, f of E minus F also has Lebesgue measure 0, and by part B, since capital F is a F sigma set, so f of capital F is also a F sigma set. So, f of capital F is also measurable, and f of E minus F is also measurable, and we know that union of two measurable sets is measurable, and we get our desired result that f of E is measurable. So, this shows that if we consider a Lipschitz function, it carries measurable sets into measurable sets. So, to summarize, what we did in this module is that we have obtained some topological characterizations of Lebesgue measurable sets. We have shown that they are nearly open or closed, and in particular we have shown that for given epsilon greater than 0, we can find an open set O containing the set E as well as a closed set F contained in E, such that mu of O minus F is less than epsilon, and this is an equivalent criteria for the set E to be measurable. And finally, we have given you an important observation by showing that if we consider a Lipschitz function f from closed interval a b to R, then this Lipschitz function carries measurable sets to measurable sets. Note that even continuous functions do not have this property, and with this we finish this module.